Hätte ich einen Punkt kommen sollen, gell?
Wer liegt an dir jetzt zum Erzählen?
Du, ich bin ein schlechter Witzeerzähler.
Okay.
Mhm. So.
Okay.
Yeah.
So then, now I switch to English. Ladies and gentlemen, esteemed representatives of business education and research in and outside the Softwarepark Hagenberg, a warm welcome to all participants of our second Hagenberg expert event on prescriptive analytics. Today, we especially focus on PA in production. To put it simply, prescriptive analytics is used in production to optimize different production tasks. However, this optimization can focus diverse, sometimes contradictory goals like energy efficiency, throughput, punctuality, costs, and so on, or some kind of multi-criteria combination of these or similar goals. To reach them, a hybrid combination of different optimization techniques with simulation and machine learning is used. Today, we would like to show you some examples from research and industry and discuss together which new perspectives arise in planning, maintenance, and real-time operation. I would therefore particularly like to welcome today's speakers who cover these topics perfectly with their expertise. These are in order of their talks. From Ljubljana, Slovenia, Professor Dr. Bogdan Filipic, from Austria, FH Professor Diplom Engineer Dr. Stefan Wagner, and Diplom Engineer Dr. Michael Bögl. Well, this is usually the time for a warm welcome applause to our speakers. I think we should try that. At the top of your MS Teams window, there's a symbol showing a smiley rising the right hand. Do you see it? If you see it, if you move your mouse pointer over it, then different symbols appear in the menu. One of them is showing clapping hands for applause. So please feel, it works. Try it. Okay. So additionally, I want to inform you how we handle questions today. After the talks, we have planned a time slot for a joint discussion with our speakers. You can ask your questions at every time using the chat function, or you can raise your hand virtually after the talks during the discussion. I call you at the appropriate time. Please remember to turn off your microphones again when you're not at the word. So before I hand over to Michael Affenzeller for his welcoming words, I would also like to inform you that this event is being recorded. Okay. Michael, the floor is yours.
Okay, also from my side, a warm welcome to all of you who will participate in this second event in our series about prescriptive analytics with the specialization today about its application in the production area, where from my point of view, it's a very obvious way to go to use PA techniques for production purposes. As we all know, digitization is all around, but with prescriptive analytics in some way, we go the next step to make things analogous again, because we try to transform it into the real world. So the findings which are taken from the benefits of digitization are aimed to be transferred back into the real world. There are two things which I want to draw your attention on, especially one of which is the annual magazine of the Softwarepark, which this year is dedicated to our main topic, which is prescriptive analytics. And I have one here, but we also have it in a digital way. And the good thing to our English event is a couple of days ago, since a couple of days, we have the English version also of this magazine. So please feel free to have a look at it. I will put the link in the conversation chat of this event afterwards. And a second issue where I want to draw your attention on, which is also dedicated to the field of today's topics, which is about prescriptive analytics in production, is the international conference, which will be held again in Hagenberg. In 2020, it was held virtually. The international conference on Industry 4.0 and smart manufacturing, the ISM 2020. And I think it's a good audience today also for participating at the conference, because the ISM addresses both persons from the field of academia as well as persons from the field of industry. In the virtual edition 2020, we had more than 100 B2B meetings and also more than 100 active participants, but nevertheless, it's aimed as a hybrid event for practitioners as well as for the academia. The scientific key points are pretty good. So all accepted papers are published in Elsevier open access publications, and we also had and will have special issues of well-reputed journals with impact factors up to 10 for selection of best papers of the conference, which is quite okay from my point of view. I also will put the link to the conference in the conversation chat. Okay, so for the moment, that's all of additional advertisement for PA and its applications in the field of production, especially today, which I wanted to share with you. And now the focus should be on the talks, and I'd like to hand over to Thomas again.
Okay, thank you, Michael. Now I would like to introduce you to our first speaker, Professor Dr. Bogdan Filipic. Bogdan Filipic is senior researcher and head of the Computational Intelligence Group at the Department of Intelligent Systems of the Josef Stefan Institute in Ljubljana, and he is also associate professor for computer science at the Associated International Postgraduate School. He received his PhD in computer science from the University of Ljubljana. His research interests are in computational intelligence, evolutionary computation, and stochastic optimization. He focuses on evolutionary multi-objective optimization, including result visualization and constraint handling. He published 46 papers in peer-reviewed scientific journals, 6 chapters in scientific monographs, and 130 papers in conference proceedings. His lecture today is titled Predictive Modeling and Evolutionary Optimization for Efficient Product Quality Control. Dr. Filipic, may I ask you for your contribution? Are you ready?
You're mute. Sorry.
Yeah, okay.
Okay.
Can you hear me now?
Perfect.
And let's go to the projection mode. So I think we are ready now, if you see the shared screen as well.
Is everything all right? Thank you very much.
Okay, so first of all, thank you very much for introducing me. I'm really glad to be able to share some of our experience in the area of applying the methods that are the topic of this event today. First of all, I would also like to say I'm grateful to Michael Affenzeller for inviting me. So, as it was mentioned, I'm with the Josef Stefan Institute, and this institute is the largest institute in the area of natural sciences and technologies in Ljubljana, and it is really a very interdisciplinary institute. It includes departments ranging from physics, chemistry, environmental science, to energy, and of course to several ICT departments. So I'm with the Department of Intelligent Systems, and I am in charge of the Computational Intelligence Group. So I was very happy to hear some keywords in the opening, above all optimization and multi-objective optimization, which are the core of my research interests. But regarding the audience and the scope of this event, I'm also glad to hear that both academics and practitioners coming from industry are attending it. Because in preparing for this event, I was thinking of which side will be represented more. So, of course, I'm coming from the academia side, but part of our work is related to applied project as well. So I would like to share the experience of how to bring these two worlds together. Not only some technical details, but also some challenges that are met in applying the methodology in practice, and some lessons we learned in case studies. Okay, so what I plan to do today is say some words about the background, the scope of our work, and then present the industrial partner to you, the one that we worked together on a specific task of developing a quality control procedure. And I would like to then go to presenting this case study in more detail, and as already mentioned, conclude with the typical challenges and lessons learned in these approaches. So it was mentioned the computational intelligence group that I work with. So my background is, of course, in computer science, and the starting period of my research career was on classical AI, including expert systems, machine learning, qualitative modeling. And then the notion of search that you all know is one of the key concepts in AI was the one that really I became more interested in. So at some point, I also switched to stochastic search techniques like evolutionary algorithms. And then, of course, these techniques are very much suitable for optimization. And based on this, let's say, essential technique, I can summarize the work of our group in this domain as shown in these four graphs here. We work a lot in multi-objective optimization, which is something that that is a topic that is very relevant for practice, although at least at the time of my education, there were little or no lectures in the educational process on multi-objective optimization. Typically, everything was single objective. But of course, when you turn to practical applications, several objectives come into play in most cases. So one thing is multi-objective optimization in general. We work on algorithm extensions, then distributed multi-objective optimization, optimization based on surrogate models and things like that. Then we are also very much interested in visualizing the results of multi-objective optimization. Those familiar with this topic will know the issue of Pareto optimal fronts and their approximations, as we see some examples in 3D space here. At some point, we got more interested in visualizing these results, so we also provided a taxonomy of a number of methods that are available for this purpose. And in the recent years, my colleague Taya Tushen and I were giving tutorials, for example, at Gecko conference on this issue. A more advanced topic we work on is the topic of constraint satisfaction in multi-objective optimization. And there we also work on improving the concepts of violation landscape analysis and similar ones. So this was on the side of research. Of course, we also transfer our knowledge to practice. And this slide summarizes some areas of applications or industrial and applied project we do in our group. So we like to say our projects are devoted to some very small components or items like the ones here at the top left, which will be discussed further today. These are small devices called commutators, which are intended for automotive industry, and this is maybe a centimeter or two in a diameter. We work a lot for manufacturing, specifically for steel industry, like for optimizing the processes there, or for engineering design. An example of a project is multi-objective engineering design of energy supply systems. But we don't stop here. The dimensions are much larger. Sometimes we also work for space exploration problems. This last figure is from one of the studies we provided together with the colleagues from JAXA, from Japanese aerospace industry, in optimizing and visualizing trajectories for some space missions. So in summary, we do both basic research, we do applied research, and of course teaching as well. For example, I give courses on evolutionary algorithms and multi-objective optimization. So this was to say a few words about the background, the scope of our work. So when it comes to applied projects, I decided to select one of them today and describe how we perform, how we deploy prescriptive analytics methods in these projects. So first of all, to be honest, I must say I was typically not selling, so to say, the approaches we work on to potential customers under this name, but being invited to this event, I digged a little bit more into this topic, and I now know that prescriptive analytics, at least as formally treated, is understood as the final stage of business analytics and relies on two other subfields, descriptive and predictive analytics. And the idea is recommending decisions using simulation, optimization, and also other tools, as it was mentioned in the opening. So to this general idea of prescriptive analytics, I would like to add the frequently met scenario, which comes from the projects we worked on, or from applied and industrial projects. So typically there is a kind of a simulation problem or task to be solved in usually in some real-world environment, for example, at a manufacturing site. So the question is, of course, what methodology to use, and it is very often that we find the simulation-based optimization concept very useful. So in practice, it is rarely that a problem is given in some explicit or analytic form. Typically, optimization, of course, when it comes to computer-assisted approaches, is based on some simulation model. For example, a model of a process you are optimizing or a device you are trying to optimize in some sense. So in our experience, it's these two essential, let's say, components, and the methods we usually use for optimizing are iterative. So starting with some initial solutions, we perform iterations where the simulation model actually acts as an evaluator of potential solutions. Once the simulation is run, some cost measure is extracted, and this is information for further loops of the optimization procedure. And then sooner or later, we end up with the optimized solutions. Now, this is, of course, a very general idea or overview. Now, I would like to move to a specific case study where such an approach was used. And this is a company called Collector, which is one of the, let's say, big international partners. The headquarters and some production units are located in Slovenia, but they have their units worldwide. They have a wide production program, including mobility components and systems, and also other fields, power engineering and technology systems. Now this one is emphasized here, so they produce various components for automotive industry. And this will be actually in the focus of our presentation of this case study today. So they produce various components for car industry, some systems or some more elementary components. And the one we will be focusing on today is a component called commutator. We have some images here. Now this is actually a component that is part of electrical motor. Not every electrical motor of specialized that are typically used in car industry, for example, you find them in fuel pumps and similar applications. So this company actually produces huge amounts of these components for various major car producers in the world. Actually, they have the world highest share in producing these components. Now, but of course, the pressure for reliability and high quality of these products is, of course, high. It is increasing, and the manufacturer also wants to have some, let's say, quality control based on advanced concepts, because this is a kind of a certificate. Their production will be more reliable, and this is also something they want to, let's say, show to potential customers. As it was explained, part of the electrical motors we are focusing on is shown in more details here, and this is actually shown in this figure, where two parts are two materials are coming together. It's copper and graphite. So and this is actually produced in a sequence of steps, and various steps are subject to quality control. Now, the idea is the following. As the stages of producing these small parts are taking place at these different stages to the production, some of them are critical from the point of view of ensuring high quality of these products. So these stations, so to say, parts of the production line, shown more closer here for one of them. The idea is that at some places, the quality control can be performed using machine vision. Now, at this point, I need to say that this company has its own machine vision group. We are no specialists for this field, but it was a close collaboration with their machine vision group and our group that works in computational intelligence in developing some quality control procedures for manufacturing this product. Of course, the idea was to inspect not all the products, but just samples of them with some optical system, capture images and extract some features and use these to inspect the quality or to make predictions about the quality of these components. Okay, so this is the overall idea. Now, two stages of producing this component, this commutator, were of special interest to the company. One thing is the inspecting the copper graphite joints. So in this case, the task was to predict or to assess what they call a quality class. So one class, of course, they like it most, is that there is no defect, but several types of defects may appear at these joints. And the idea or the requirement was for the machine vision based control system to assess, to predict the class of the quality class based on the images. There was another one even more challenging, namely this commutator has what they call a mounting hole. So here comes here is a hole that serves for mounting this commutator on the axis. And the idea here was, again, based on machine vision, to provide a kind of a system for non-contact measurement of this roughness. Namely, this hole must have just the right roughness in order to provide fixed positioning of this commutator later on when it becomes a part of the motor. So it will be detailed further on. So from now on, I will focus on this task and show where and how our methods were applied. So the idea or the overall scheme of the quality control procedure, well, actually for both tasks, was this one. We start with the image of the product taken from the line. We perform some image preprocessing, and then we apply a machine vision system which extracts images from these images of products. And then we use some machine learning model, predictive model, that predicts either the quality class in the case of assessing these classes for joints, or predicting the roughness in the second case. So the overall scheme is the same. Now, of course, this is a general concept you see at various places, but of course, developing such principle is subject to certain technical details, and I will be discussing some of these, actually explain how we approached this task in our case. So first of all, I need to be more specific about this machine vision part of the problem, where the situation goes like this. Of course, we have online image capturing and we have image processing, and this is all based on a certain manual setup. There is, of course, let's say, machine vision specialists and people from production set these procedures, these steps in a certain way, typically based on the experience on previous applications. But there are certain further steps that are expected to lead to such a, let's say, model that would then act as a tool for assessing the quality automatically. And one thing is the attribute extraction based on processing these images, which requires some machine vision system settings as well. Typically, what you have here is a sequence of image processing operators, various filters, processing, things like that, and they involve certain parameters. Again, they can be set by, let's say, experts, but the idea in our case in designing such a procedure was to tune these automatically, to be subject of optimization. And of course, once you have these attributes of an image of such a product, you would like to build a machine learning model, which again involves some parameters. So building or applying machine learning is always based on some method that also involves certain parameters. And again, this is part of the automated procedure. We would like to end up with a certain model for predicting either the quality class or predicting the surface roughness. And of course, this raises the question of optimizing these two steps. Now, so if I now show the overall approach of optimizing this quality control procedure, in total, it works like this. So this is now something that is, if the previous scheme was showing the idea of applying the method once it's developed, now here I show how we came to this procedure, how we optimized it. So the idea was to involve a number of methodologies. First of all, of course, machine vision for capturing, preprocessing the images and extracting the features, and then machine learning as well for learning predictive models based on the features of the images. So we start with a certain set of original images. We process these images, extract some regions. This is all part of preprocessing, and then machine learning and machine vision settings are something that is optimized in this loop. So actually, based on the general scheme that I showed before, so we have a loop of optimizing a certain process. In this case, the subject of optimization are parameters of machine vision and parameters of machine learning algorithm. So now the evaluation goes through these steps. So once we have a settings, let's say as a candidate solution, a vector of settings for both steps, we first apply the machine vision algorithm. It extracts the attributes. We then apply the machine learning algorithm, and then a machine learning model is constructed, and we also get some model error, which is based on internal testing, for example, on repeating this learning procedure and then performing cross-validation procedure. So this runs in a sequence of iterations until a certain stopping criterion is met, and then the result of this procedure is twofold. On one hand, we have the best found prediction model for producing, let's say, the predictions. Okay, in this case, RZ is this roughness. It also can be producing or assessing the quality of the joints in the second application. And as a side result, there is also the best found machine vision and machine learning settings or parameter values. So this is the idea. Now some additional details on these are as follows. So regarding the optimization procedure here, of course, since we are very much involved in evolutionary computation, we used an evolutionary algorithm that acted on vectors of parameters of these two methods. So machine vision for extracting features, typically there was an order of 5 or so parameters, various thresholds and settings for machine vision, for image processing, and also a machine learning algorithm, depending again on which one was used. So typically, let's say, regression trees and random forests for predicting roughness, for example. So in total, again, for this machine learning part, about 5 parameters, something like that. So in total, this could be seen as a numerical optimization problem of, say, about 10 variables, but evaluating these was subject to this a relatively complex simulation procedure. And of course, then while this was iteratively improved, it resulted in the two components that I mentioned. Okay, so this is just a bit of an insight into the optimization as it was proceeding in this case. So what we see here is actually how we can optimize the predictive models, regression trees or random forests for predicting this roughness, which was part of assessing the quality of these commutators. So what we have here is these two fixed lines are the, let's say, the errors of the predictive models based on non-optimized values of parameters. So it's for two kinds of methodologies or predictive models. It is for regression trees and it is for random forests. of course, these are constant values. It is fixed values of parameters. If we optimize the parameters of machine vision component and machine learning component of the quality control procedure, we can improve them as it is shown here. So one could apply some expert settings, but quite clearly this plot shows there is room for improvement if on top of machine vision and data mining or machine learning that are really needed, if we on top of that plug in optimization which tunes the procedure. So okay, this is actually not just an academic approach to it. This was in fact installed on the production line as part of a project that was carried out. It was an international project under the Artemis project call, where the collector company and our institute participated with this use case of developing the quality control procedure in the way that I briefly described, and demonstrating it successfully. So what is the status now is this prototype has on one hand been shown that it can really help in automating this quality control because it is based on an optimized procedure, and it is capable of controlling more parts than it was done in the past. So they are still doing sampling, not controlling all the products, but the quality increases. Now, from the academic side of the task, there is something that is also interesting, and the colleague from the company is working on this now. And just as an idea, in this project, we were optimizing the procedure from the point of view of tuning its parameters. Now, if you think of the machine vision part, the image processing, there is a number of, let's say, operators involved in it, and it is also a matter of their sequence. So these colleagues is now interested in tuning not only some parameters, but also, so to say, the topology of this procedure. So he is trying to answer a more general question, not just what are the most appropriate parameter settings for this vision-based procedure, but also what are the appropriate operators for image processing and their sequence. So he works on genetic programming for actually designing these procedures entirely automatically. Okay, so this was to say something about the examples, and I would, about the specific case study. And I would now like to conclude with some challenges that are typically met in applying predictive or prescriptive analytics in practice, and some lessons learned on our cases. So it is very often that there is different understanding of these tools and also different expectations from them when the two sides come together. That is the solution provider and the user. And of course, typically there is insufficient knowledge, and I'm saying this from experience of bringing, let's say, achievements of academic projects, of research projects to practice, to industrial projects. So it is, on one hand, insufficient knowledge about the problem domain by the solution provider. Let's say if an academic team tries to apply the methodology in practice. And on the other hand, the concepts of these tools by the users. Now, as already mentioned, it is very rare that problem formulation is given in advance. So formulating the problem in such a way that it can be handled by some formal methods is typically a significant part of the optimization project, or one could even more widely consider this of applying tools of prescriptive analytics in general. So real-world problems differ from those in textbooks. I guess most of you will agree with this very much, but I'm telling this very often to my students because at an earlier stage, typically you're very much interested, and young people are very often fan of certain methods. But of course, I mean, when it is a problem in textbooks, in papers, we usually start with problem formulated or in a formal way. In practice, there is rarely such a thing. Now, the optimal values of objectives are typically unknown, and this makes the results assessment difficult. And this is true for all kinds of target values we want to achieve. In practice, there's rarely the situation as in artificial test problems where the optima are given and developers of techniques, algorithms are trying to come as close as possible. And the final one has to do with the subjective issues. From our experience, even if a certain approach probably produces positive results for the user, it may still not get adopted in practice because of various non-technical issues. So this is also something that one has to have in mind, even let's say, successful approaches, successful from the point of view of, let's say, academic research or technically speaking, but for these subjective non-technical issues, it may still not get adopted. And so finally, about the lessons learned in the examples of this kind. So we usually approach this kind of projects or challenges in a sequence of steps. And the first one is very important. I would say this is educating the users about the methodology. And on the other hand, we need to acquire a certain necessary domain knowledge. This is how the two words come together. So as a precondition for a successful project, in all our, let's say, successful applied project, I would say this was in the first place an interdisciplinary team of both experts from the problem domain and experts in the methodology, of course. Motivated individuals are crucial for successful project in particular, and I'm looking from our side, from the side of academia now, having someone on the side of the potential customer who was very much interested in some way for the success. This was always very beneficial for the project. For example, someone who is also let's say, interested in the more research side, like obtaining a PhD or even or master degree on the topic of the project. And the final part of the lessons learned, so this is related to evaluation. The measure of success of a project should be clearly defined. This is to avoid misunderstanding towards the end where the situation becomes more critical. So, and by the measure of success, this has to do most with optimization, but I think it's important that the measure of success is defined both in terms of the result quality and the method efficiency. So what should be the quality of the results and how efficient should our methodology be? So is it the matter of milliseconds, or is it some offline approach that can take a significant amount of time? I would say one of the messages is in these kinds of deployments of the methodology in practice is also not to emphasize the methodology when interacting with the users. The situation is very simple. They are interested in solutions to their problems and not in the algorithms or methods themselves. So again, looking from the point of view of academia, I think that promoting success stories of this kind of applications is also important, because it on one hand attracts further interests and also helps to bridge the gap between the two sides. So as an illustration, this project was actually an industrial project that resulted in an industrial prototype, but on the other hand, it was also a subject of some research on our side of how to avoid overfitting in tuning these models, and this was published as a research paper. So with this being said, I see my time is over. I apologize for being a few minutes late. I would just like to conclude with the acknowledgement of some colleagues of mine from the Institute and the 2 colleagues from the collector company, and of course the company itself, our Ministry of Economic Development and Technology that supported this project, together with the European Artemis Industry Association. So this really brings me to the end of my presentation, and I wish to thank you for your attention.
All right, thank you very much, Dr. Filipic, for your vivid presentation and for the examples. You mentioned that the real world problems do not meet the textbooks, or the students do not have the possibilities to find the real world problems in the textbooks. But I have seen a lot of students in our audience now, so they have the possibility, and that's also the reason why we do events like that. Okay, I just want to mention that we do the questions afterwards, after the presentations in the discussion panel. And questions can be asked during all the talks in the chat room, and afterwards also they can be asked by the audience themselves. All right, the next lecturer is FH Professor, Diplom Engineer Dr. Stefan Wagner. Stefan earned his doctorate in technical sciences from the Johannes Kepler University in 2009. He has been working for the FH Upper Austria already since 2005, first as part-time lecturer, then as assistant professor for software project engineering, and since 2009 as professor for complex software systems at the Department for Software Engineering here at the campus Hagenberg. This job, of course, seemed not to occupy him in terms of time. That's why he was CEO of the FH Upper Austria IT GmbH from 2011 to 2018. His research interests focus on heuristic and evolutionary algorithms, as well as heuristic optimization in production and logistics. As member of the respective research groups, he carried out several research projects, which led to well-known open source optimization system Heuristic Lab, and finally to the Josef Ressel Center for Adaptive Optimization in Dynamic Environments, funded by the Christian Doppler Research Foundation. His talk is dealing with the topic Dynamic Problems and Adaptive Optimization, how to solve optimization problems in an ever-changing world. Stefan, the floor is yours.
Thank you, Thomas, for the introduction. And I'm going to share my screen so that you can hopefully see my presentation. So this should be now the case. And I welcome you to my talk. Thank you for giving me the opportunity to talk to you about a research problem that we are focusing on in the Josef Ressel Center adaptOp, and which is a very interesting problem also from the prescriptive analytics point of view. I can only underpin what Professor Filipic already said before regarding the challenges that we face when we try to optimize problems that the industry and economics have. And I would like to show you another kind of problems that we are especially interested in. Before we come to the core of this talk, I want to quickly give you an overview of who we are. So the research group HEAL and the colleagues I'm working with is one of the largest research groups that we have at the campus Hagenberg at the University of Applied Sciences in Upper Austria. And the research group is led by Michael Affenzeller, so you all know him. He's also the scientific head of the Softwarepark, and we do research in Hagenberg on this topic of heuristic optimization since 2005. And you see all the people that we have now in our group, 17 research associates, and we were able to gain several different research projects. And one of our main strategic goals was to have a large research project as a backbone of our group. And we were able to acquire such projects in the last years. We started with the Josef Ressel Center Heureka, which was one of the first Josef Ressel centers that were funded in Austria from 2008 to 2013. Then we had a K project called HOPL on heuristic optimization, production, and logistics. And nowadays we have two Josef Ressel centers. One is led by my colleague Gabriel Kronberger, the Josef Ressel Center Symrec, and the other one is led by myself, which is the Josef Ressel Center adaptOp. And these projects bring us a background and the possibility to concentrate on the research questions that we have quite intensively because they are funded over several years. And they also gave us the opportunity to develop a very intensive research focus in Hagenberg on meta-heuristic optimization in two different kinds of application domains that I want to show to you next. So if we have a look at the research focus that we have in the HEAL research group, then of course in its core, we are concentrating on meta-heuristics. And therefore, we also developed an optimization system, which we provide as an open source project, which we call Heuristic Lab. So it's always a little bit of confusion between what's the name of the research group, which is HEAL, and what's the name of our software system, which is Heuristic Lab. But just to give you an impression, you can also have a look at our homepage of the Heuristic Lab project. And in Heuristic Lab, we provide several meta-heuristics such as evolutionary algorithms or other meta-heuristic optimization algorithms. And we originally, as a research group, come from the development of these algorithms and from the research of these algorithms. And then over the time, we realized that of course, these meta-heuristic optimization algorithms can be applied in different domains. And one of these domains is production, logistics, optimization, and operations research. So in fact, we're doing similar projects that also Professor Filipic is concentrating on and that also some other colleagues in Hagenberg are working on. We try to provide algorithms that can help the industry and that can help manufacturing companies to do the right decisions at the right times. And on the other hand, we also have another application domain, which is dedicated to machine learning and to database modeling. And of course, the application domain of operations research problems and algorithms and machine learning algorithms seem similar, but the techniques that you use are quite different. So it might be sound strange that we have these two research focus points together in one research group. And the reason is this common core in form of evolutionary algorithms, genetic algorithms, and also genetic programming, which we have in the meta-heuristics that we are researching on, which brings together these two fields. And what we are going to see also in this talk is how these two fields very nicely fit together and work together when it comes to prescriptive analytics and when it comes to solving hard optimization problems in production and logistics processes. So first of all, I want to quickly show you the typical problem-solving workflow that we use, and not only we, also many groups around the world use when it comes to solving optimization problems. So first of all, we start with a production, for example, a logistics situation in reality, and then we see there is something where we want to apply optimization on, so we need to do this workflow of conceptual modeling so that we get a conceptual model of our problem. Then we have to transform this conceptual model into a scientific model. This scientific model then hopefully can be solved with different algorithms to acquire a solution, and then this solution gets implemented in reality. And I personally, as a researcher who is interested in meteoristic algorithms and in solving hard optimization problems, of course, I am very much interested in this step of model solving here. So going from the scientific model that we have to the solution, but which was also pointed out by Professor Filipic, the whole cycle is very important to operate successful projects, because we first of all have to come to a scientific model that then can be solved, and of course we also have to take care how to implement the solution in the end in reality. And now what's interesting with this conceptual workflow, of this problem-solving workflow, when you have a look at production logistics processes in companies out there, that these problems that we want to solve do not have to be solved once, but they have to be solved round and round again. Because if you think of a production process where some good, for example, a steel slab is produced, and you have to do a decision where to put this steel slab after casting in the hot storage area, then this decision problem that you need to solve has to be solved all over and over again every few minutes when a new slab just comes out of the continuous caster. And this is something which is especially interesting when it comes to this optimization problems and methods that we apply, because we have to take care, and we have to keep in mind that we do repeatedly solve these problems, and we should think about what we can reuse of the information that we used in previous problems that we solved to maybe gain better or solutions more quickly. So I would like to present you one of these production processes that we are concentrating on, which is the process of transporting casted steel slabs from the continuous caster to the rolling mill. And this is the process of one of our partners in the Josef Ressel Center, adaptOp, which is voestalpine. And this should give you a better understanding of how these processes look like in reality. So here you see a picture of a continuous caster, and you see the hot steel slabs coming out of the caster, and they are then picked up by a crane and stacked here in the so-called hot storage area. So the area where the freshly casted steel slabs are parked is called the hot storage area. The steel slabs have to cool down a little bit so that they can be transported with other transport means. And then they can take different ways throughout the plant to the rolling mill. So we want to transport these hot steel slabs to the rolling mill. Some of these slabs can be transported still as hot slabs directly to the rolling mill. Of course, some have to be put to a local storage in the meantime, then they cool down, and then later on they are again picked up and transported to the rolling mill. There they are warmed up, and then they are pushed into the mill. And of course, also some slabs have to go through some processing steps. For example, it can happen that the slab has marks due to the casting process, and these marks have to be worked on so that the quality of the slab is increased. So these post-processing steps are also maybe required. So another way through the production process is to go through these processing steps. And of course, it can also be the case that you have to first bring the slab to storage, and then to processing, and then to the rolling mill. And then there are several transport means that can do this transportation of slabs. So we have straddle carriers, like the one on the left-hand side. We have reach stackers, or we have small trucks and trailers that push, that pull the slabs through the whole plant. And you see in this small process, in the much larger process of producing steel, that there are several decision processes and optimization problems that you can concentrate on. We have a stacking problem here, for example, so we have to decide which slabs are put where in the hot storage area. Of course, we want to do that in an optimal way, so that slabs that we need earlier in the rolling mill are not overlaid by slabs which we require later, so that we have to dig them out again. We can solve a storage location problem here, so where to put the slabs in the large storage area. Of course, there are many of these storage fields. We have a transportation problem here, so which transport vehicle is picking up which slabs and which route do they take. And of course, we also have scheduling problems to solve. So the sequence, how the slabs are casted, the sequence, how the slabs are rolled, and also the sequence, how processing steps are scheduled are also decision problems that we have to solve, and where we want to find an optimal decision in all these cases. And now I would like to pick out one of these decision processes, and this would be stacking the slabs after they are casted. And if we think about traditional optimization in this case, how would this be optimized? So we have a dynamic production process where the slab is casted, and then an event occurs which says us, okay, now there's a new slab at the end of the continuous caster, and this new slab can be picked up, and we get an event that now the optimization has to be done, because now we have to decide where this slab should be put in the hot storage area. So we have an optimization problem to solve. What does that mean? We have to transform the data that represents the slab and the status in the hot storage area, so where all the other slabs are currently stacked, and where the crane is currently moving and so on. And we have to transform this data into an optimization problem. This, of course, is this transfer from the reality to the scientific problem. And then we can use some kind of optimization algorithm, such as a evolutionary algorithm, for example, or a branch and bound algorithm, or any algorithm to acquire a solution. And then we transform the solution back into a crane assignment and tell the crane, okay, now pick up the slab and please transport it to this and that location, because this is the best location for this slab to be stacked on. And of course, we're talking about difficult optimization problems here, complex optimization problems. So solving these optimization problems takes some time, and this is visualized in this long arrow here. And you see that on the x-axis we have time here. So we want to spend some time on solving this optimization problem, because the more computational time I can invest in finding a good solution, the better the solution hopefully will be. Of course, we cannot spend too much time on that, because if the next slab is coming out of the caster and the slab which is waiting there for being picked up is not removed early enough, then we get severe troubles. So now in this classical optimization scenario, what can happen? It can happen that quality control, which takes place after the slab has been casted, comes to the conclusion that the currently casted slab has some problems and requires post-processing, because there are some marks in the slab, for example. And that's a difficult situation, because also this quality control step takes some time. And it might happen that the result of this quality control is that the slab has to take another path in the production system, so that we cannot go directly to the rolling mill, for example, but we have to go to post-processing of the slab first before the slab can be rolled. And this means that the situation changes. So the assumptions that we made when we started the optimization algorithm to find the optimal position for our slab, these assumptions are not true. And in fact, this means that we compute a crane assignment here on the wrong assumptions, which renders this solution that we find here useless. And this is the problem that we are concentrating on in our Josef Ressel Center, and this is also, in fact, a problem of dynamic optimization. So how can we deal with such optimization problems where we cannot be sure about the situation that we currently have, and where the data and the situation in the production process might change when we solve our optimization problem? And usually the optimization algorithms that we can apply and that are often used are not very happy when you start to change the problem data and the assumptions that these algorithms have about the real world when they are solving their optimization problem. So what can we do to solve such dynamic optimization problems, of course, we have to apply prescriptive analytics. And in prescriptive analytics, we have these three core technologies, which is optimization on the one hand, so meta-heuristic algorithms or also exact algorithms such as evolutionary algorithms, branching bound algorithms, whatsoever. We have to apply simulation to be able to predict the future somehow, and we have to apply machine learning to draw some conclusions out of the process and the data that we observe in the production process. And these three technologies have to be brought together into what we call an adaptive optimization system. So what's the vision that we try to reach in our Ressel Center? We want to have an optimization system which is not executed sequentially. So when an event in the production process occurs, then we start our optimization algorithm, and then we get a result, and then we do what the optimization algorithm told us to do. But we want to see optimization as a continuous and adaptive process. So in parallel to the dynamic production process, we want to start our adaptive optimization system, which then receives change events from different situations that occur in our production process, such as a new slab arriving at the end of the continuous caster, or information from quality control that the slab needs some post-processing, or other changes that might occur. For example, availability or failure of a transport vehicle is also a dynamic event that can occur and that can take place. And then we want to draw conclusions from these continuous changes that we receive, and we want to feedback actions to the dynamic production process. What would be the best action to do next? And to be able to develop such an adaptive optimization system, we need three parts. First, we need a way to describe the dynamic nature of the problems. So we do not only have to find scientific models for the decision problems that we want to solve, but we also have to take into account that these problems have a dynamic part, that they change over time, that they have to be solved repeatedly. And this dynamics have to be described somehow, and we need optimization algorithms which are able to react on these dynamic changes. On the other hand, we need machine learning to observe these dynamic change events and to predict upcoming events in the future. Because I want to have an optimization system which is able to see into the future and to foresee upcoming changes that might occur with a high probability, so that we can also take this possible different scenarios that happen in the future into account, so that we already compute solutions to these scenarios and have them ready when the specific situation really occurs in the future. And last but not least, we need adaptive optimization algorithms, which are able to take this dynamic information from the optimization problems and the inference from the machine learning algorithms and take these information together to draw the right conclusions and to apply the right optimization methodology and to react on changes during executing an optimization procedure. And that's what we want to achieve. That's, of course, is not easy. That's why we have this Josef Ressel Center for Adaptive Optimization and Dynamic Environments, which is funded for some other years to work on this adaptive optimization systems, where we identified several research challenges and goals. On the one hand, modeling these dynamic problems. So how can we identify which events are relevant for our decision problem that we want to solve? How can we trigger these events? How can we couple our optimization system with a reality, with the production information systems at the companies? And how can we pass data back and forth to react dynamically on changes that occur in the production process? Next step will be the development of reactive optimization algorithms. So we have to deal with questions how an optimization procedure that is currently trying to find an optimal solution for a problem can react to changes in the problem situation. One trivial way to react to these changes, of course, would be simply to stop what we're currently doing and to restart the optimization with the new data. But this, of course, is also wasteful because we have already computed partial results that we can maybe reuse. So we have to think about how to set up another optimization run with slightly changed data. What can we reuse from the previously computed solutions? What do we have to do once again? Then third part is integration of machine learning to predict the future, to learn from these events in order to create different optimization strategies. And what's meant by adaptive optimization algorithms is that we want to have optimization algorithms that are able to learn. We know that the different meta heuristics that we have very specific characteristics, and they are differently suitable to solve optimization problems. And we have to, for example, learn which optimization strategy to use in different situations so that we always pick the right optimization strategy, the right optimization algorithm, depending on the dynamic situation that our production process is currently in. So I would have one more slide about the system architecture that we developed and that we use in our Josef Ressel Center, but I will skip that now due to the time that already has passed. And the last word that I want to say you is that we implemented this reference architecture, the system architecture that we developed also in a benchmarking infrastructure, because when it comes to dynamic optimization problems, it's also always very hard from a scientific point of view to get benchmarks that you really can test different methods that you have or different algorithmic ideas that you have. You always need some form of simulation for that purpose, and this has to be reproducible and so on. And that's why we concentrated also on creating this benchmarking infrastructure that we use for our algorithms to develop and test them, but we also use it as a general benchmarking infrastructure for the scientific community. And we also did a competition at last year's Gecko conference, and we will also run this competition this year. So we hope that there are a lot of also other researchers around the world interested in this very difficult dynamic optimization problems, and that we can see what solution methods work best. So if you are interested in what we are doing here, just drop by at the adaptOp AT website, which will be online soon, and where you can find the details about this year's Gecko competition. Okay, so that's all I wanted to show you on our Josef Ressel Center on adaptive optimization and dynamic environments, which is a joint work with the University of Vienna and our company partners, which you see in the footer of the slide. And I'm very happy to discuss with you some questions or some comments about that afterwards, after the presentations. Thank you.
Thank you very much, Stefan, also from my side. I hope you can hear the virtual applause. Yes, this was another very impressive example how this different PA method can be used. And that leads directly to our third speaker, which I'm now pleased to welcome, Dr. Michael Bögl. Dr. Bögl is a researcher in design and implementation of combinatorial optimization algorithms for industrial projects at the RISC Software GmbH in Hagenberg since 2014. Prior to that, he worked at the JKU as postdoc in Christian Dipl laboratory for efficient intermodal transport optimization, and before that at the Institute of Production and Logistics Management. His research areas include exact heuristic and meta-heuristic solution concepts for combinatorial optimization problems in logistics and production, large-scale problems with complex constraints in dynamic environments, as well as methods for near real-time optimization in production machines. In the subject of his lecture is Prescriptive Analytics and Industrial Perspective. Thanks for the time, Twisker. Dr. Bögl, it's your turn.
Thank you very much. So I share my screen. Thank you very much and welcome to my presentation. As I have chosen a very, very general title for this presentation, I want to start with an outline of this talk. First, I want to introduce the RISC Software GmbH, for which I work. And then the main topics of this talk are two different areas. At first, I want to present two different use cases which I was involved in recently in the area of prescriptive analytics. And the third part, the last part of the talk, I want to discuss a little bit about architecture and the development process for such projects. So let's start with a brief introduction of the RISC Software GmbH. The RISC Software GmbH was founded in 1992 by Professor Bruno Buchberger, and it consisted of the industrial research group of the Research Institute for Symbolic Computation. So the backgrounds are in Research Institute, and the RISC Software GmbH has three major topics where it works. We first do software development for customers. We do the whole software development life cycle from conception, implementation, support, and further development. This is one topic we work on. The next one is applied research. We do a lot of applied research projects, especially in production and logistics, but also in medical informatics, industrial software application, and so on. And finally, we do technology transfer, which means the methods which are developed in basic research or in applied research are transferred into projects with customers, which then are really in production. And this is the point of view I want to take in this presentation. So this is, therefore I have selected two different use cases in the area of production, which I think are very interesting. The first one is a finished project. It is working and it is used since 1.5 years, I think. And I called it Digital Twin in Mechanical Engineering. And there, production machine manufacturer had to manufacture a machine which produces glue laminated timber. These are wooden boards which are glued and pressed together. This is used in construction, building construction, and so on. It has a lot of different use cases, and the machine should be able to produce a lot of different types of those timbers. And the raw material is a wooden board. And wooden boards are a natural product and can have completely different properties. For example, I've drawn two boards. The first one is a very good board with no bad parts. And the second board that I have drawn has 3 bad parts, which cannot be used in the final product. The final product has to satisfy a lot of different hard constraints to be stable. And typically, the goal was to minimize waste of raw material, which means minimize the waste of good wood. And the problem this company faced was that typically a production machine has some type of control algorithm which instructs the programmable logic controller and controls the whole machine. But due to the variation in the input, raw material input, and the output, the finished product, they were not sure that they could implement a control algorithm which could produce, which could minimize the waste of raw material. So they came to us, and we developed an optimization algorithm which is able to calculate the optimal control for this machine to minimize waste of raw material by taking the input, the properties of the input material, and calculating the optimal control sequence for the given output product. And we did this project during the construction of the machine, and the company then said, okay, we do not know how many buffers we should build into the machine. What is the optimal number of buffer places in this machine so that we could minimize the waste of raw material? And we said, okay, this is an interesting problem. We could change this optimization algorithm to take the number of buffers as configuration parameter. Then we can use this algorithm to calculate for artificial data and artificial products the waste. We said we need a lot of input data, of real-life input data, and we need a lot of different product configurations. And we did, they created these data, they gave it to us, and we did an extensive computational study, and we could show them how many buffer places should be built in the machine. They were really concerned about the buffer places because the number of buffer places increased the construction cost, and more buffers also mean longer cycle times of the machine. So the throughput is lower with more buffer places. And I cannot show you how the results in this particular case were, but what I can show you is how the results could have looked like. So these are possible outcomes, and depending on the outcome, you can decide how you want to construct the machine. Here I want to show you, for example, outcome number 3. At the x-axis, you have the configuration. This is the number of buffers: 1 buffer, 2 buffer places, 3 or 4 buffer places. And on the y-axis, there's the waste. And as you can see here, the lower the line, the more on the bottom the line is, the better the result. And you can see here that if you go from 1 buffer place to 2 buffer places, there's a huge increase, a decrease in waste, a huge increase in quality. But if you go from 2 buffer places to 3 buffer places, there's nearly no improvement. And by doing this computational study, the company was confident into making an informed decision about how many buffer places there should be there. So this was a very, very interesting project. Let's go to the second use case. This is a use case we are currently discussing with a potential customer, and it is forecast and production, integrated forecasting and production planning. It is a make-to-stock production company with highly seasonal products. You can see this on the left side of the slide. Here are on the x-axis are the months, on the y-axis is the sales, and you see that this is highly seasonal. And the black line here marks today. So everything left of this plot is the past. So this company has to produce or has to make the product only on the forecast. They have a forecast and they have a limited production capacity, and they must decide today how much do they produce and how much will they sell in a year in the future. So this is the forecast. This can be calculated by forecasting methods, or it can be calculated, or it can be created by experts, or a combination. And this is the basis. They know they have some forecasting error, which gives lower and upper bounds, and somewhere in between there will be the real demand. And they have additionally the actual orders. The actual orders for next month nearly meet the forecasted demand, but the actual orders for in a year deviate much from the real demand. And now they have the problem that they must start production now for the demand in 1 year, because they have a limited production capacity. Then they have a complex product mix. They have long procurement lead times, and this is what the next 2 points make it very complicated. They have interdependent production processes. They have a few machines which are bottleneck machines depending on what product mix they are producing. And they have multiple factories where they can decide where to produce certain products. And they have this discussion. The financial department does not want an early production start, because this means capital commitment, and maybe they produce too much. And the production department says we want to start now because now we have production capacities. Maybe if we start too late, we cannot we cannot meet the demand, and we have out of stock situations. This is also bad. And so there's this discussion between the two departments, and here's the plan to use prescriptive analytics to decide when to start production, so as to minimize, for example, the capital commitment, but to avoid out of stock situations in case in 1 year. And here we are in discussion how we will do this. And if you have such a system, you can, every time you change the forecast, you can recalculate these times. This is a rather fast calculation, and you can be sure, you can now see if you're going to run into a problem capacity-wise or elsewise in 1 year. And this is an area which is, in my opinion, very interesting, because the companies then have some foresight what they can expect in the future. Okay, these were my 2 use cases, whereas I think rather interesting from a practical point of view. And now, in the last few minutes, I want to go on to another topic, which is often a discussion with customers. One is the architecture of such a prescriptive analytics system or the platform, and the other topic is the development process. If it's possible, we prefer this architecture, which is depicted here. On the left side, you see the infrastructure of the customer. Customers often have some type of data collection and management, Oracle, Microsoft SQL, any database. They often have some type of planning and execution system, SAP, Microsoft, Oracle, Excel, and a prescriptive analytics platform, or the tools we develop for them, should seamlessly integrate into their system. And we prefer this design, that these prescriptive analytics services are separated from their system and connected via a defined interface. And we often do a service-based architecture, which suits this type of problem perfectly. We have a defined interface and we have different capabilities. For example, we have an optimization service, which does rough production planning. We have a model prediction service, which does the forecast. We have a model training service, which trains the forecast model, for example. And every capability in here can use state-of-the-art libraries, tools, or frameworks. Today, for example, it's CPLEX. In 10 years, for example, it's Gurobi, which should be used, which is state-of-the-art. And you can very flexible add services, and you can very flexible remove services or change services or adapt services to new needs. So this is these are the main advantages. Other advantages is if you use container environments, then you can run these services on premises, local, at the customer, at their sites, or in case, for example, for model training, the computational resources are not available on premises, he can move this service, this capability into the cloud, into a private cloud, or somewhere else. So with a service-based approach, it is very flexible, and in cases where we have adapted it, we are very happy with it. And there are a few drawbacks. If you have a huge data set which must be transformed, it is most often better to bring the capabilities which need the data closer to the data collection of the customer. So even this is the architecture we want to achieve. It is not always possible because every customer has completely different needs in this area. And the last slide I want to show you is the development process. And there I must say that the first presentation of Professor Filipic, his last slide, meet exactly the same I want to say here. Typically, when we develop such a product for a customer, we have some project initiation with a initial kickoff analysis workshop where the customer states his problem, tells us his goals, which data is available, how does the IT infrastructure look like, what are the requirements, and how do the constraints look like. And there we have to establish a common language. We have to find the language of the customer, and the customer has to find our language. And typically we meet because everybody is flexible enough. And after this, in this phase, also the architecture solution approach, the technology stack is defined, and the process model is defined. And then we develop a solution in close cooperation with the customer in multiple cycles. And after every cycle, the customer gets a working software where he can test the features we've implemented and can give us feedback for further development. And prescriptive analytics projects are complex projects where this feedback is very important for us to understand the goals of the customer better, but the customer must also understand the methods that are used. And so this is an iterative cycle. And finally, yeah, the release can go into production, and then perhaps an additional project is started. So this was my last slide. Hopefully this presentation was interesting. I tried to bring some industrial perspective, what in industry we are working on currently, and how do we do such projects. So thank you very much.
So, Dr. Bögl, thank you very much for your very interesting presentation. Please leave your camera switched on and we directly go to our virtual panel discussion. I would also like to ask the other presenters, and yes, Michael Affenzeller, you're all here together. Okay, so we can start our virtual panel discussion, and just as a kind of warm-up questions, I think it's quite interesting. On the one hand, in the beginning, Dr. Filipic said, okay, the methods should not be emphasized too much. On the other hand, Dr. Bögl says the customer must know them. That's very interesting to me. So what should we do now? What aspects or techniques are particularly important in PA? Maybe, Michael, you haven't talked too much today. May I start with you?
Well, I think both sides are on their right, and I think it's somehow we have to distinguish also to what extent the user, the domain expert, is able to achieve insight about the internal functioning of the method. So this all has to do something about also with explainability and interpretability, not only on the side of the results, but also on the internals of the methods. And what we have observed in our project, that those partners who have a background in computer science and mathematics can be additionally motivated or identify maybe even additional problems that might be optimized with similar methods, which we wouldn't know from the algorithm sides if they know more about the method. But of course, as more it comes on the management level, the more the focus is on the results and the benefits and the percentage of gain or energy that can be saved.
But in your opinion, which techniques or which aspects are particularly important in PA?
So I think it's the combination of techniques which leads to the additional benefits which can be achieved. And one of the major challenges is that on the one hand, we need the integration of several rather sophisticated scientific disciplines and fields. And on the other hand, we have to go deep into the topics. So I think the key issue is team playing in this field of research, to bring together experts from with a deep knowledge in the field of simulation, optimization, artificial intelligence topics and machine learning, to really use this toolkit of prescriptive analytics well. And that's also has been one of the reasons why I think that the Softwarepark is especially suited for going on with these topics, because distributed among several university and other research units and companies, we have a lot of this kind of expertise and know each other that we can use and apply and further it together.
Mm-hmm. Thank you. Dr. Filipic, what do you think, which aspects or techniques are especially important from your point of view?
Well, so I also think it's the combination. Again, in my experience, most of our projects were, of course, regarding the methodology optimization based, but many of them also in combination with some data mining techniques. So various kinds of predictive model building. But I would like to add on the previous issue of whether or not to emphasize the algorithms. So indeed, it has to do with the level and with the background of the, let's say, counterparts. So let me just remind you of, let's say, at least some time ago, there was quite a reluctance from many customers regarding the application of meta-heuristics or stochastic search techniques in general, because of their perception that they are not that okay because they really don't ensure optimality. They may return different results at different runs and so on. So I think this has changed over the time, that there's more of this methodology around, and also the awareness that sometimes this is the only way of solving the problem. You cannot always solve it optimally. So, and I guess there is something similar nowadays. Nowadays, all these deep things are popular. So I'm not that much in following what's the perception of these in practice, in real world applications. But my guess is that sooner or later this will be something, if it is deep, then it is good. But
Okay.
maybe we just need some more time.
So I think
it's, yeah.
Sorry.
It's
I think
okay.
that's an interesting point you mentioned. Well, these deep things are popular. When you see the different applications in the industry, are these current AI megatrends, deep whatever, that relevant for industry, especially manufacturing? Whoever wants to answer, everybody is asked. What do you think? Michael Bögl.
I think production is a very large field. So as we have seen in the first talk, machine learning is in computer imaging very, very successful in other areas too, and there are approaches to bring these methods closer to planning of production processes. And I think this transfer from one field to another field, a completely different field, takes some time. And production processes are at least the production models, optimization models for production processes can be formulated, and methods to solve these problems are developed since 60, 80 years, and they're very advanced. But using deep technologies, I think you can extend the capabilities of such methods in some way or another.
Mm-hmm. Okay. Stefan, would you use deep learning methods in the steel production for the slabs or for whatever? What do you think? Do you use them, or should they be used in future?
Of course, they can be used and they should be used. We are currently starting to focus on this machine learning topic also in our Josef Ressel Center now, and we are open for all different kinds of machine learning methodology that is out there. And I would say there are specific situations where also all the deep whatsoever technologies are very, very strong, especially when it comes to to unstructured data where I do not require a model to be somehow understandable. If I just need a model which predicts an image, and I do not want to understand how this prediction is done, I'm just interested in the result, then of course a deep neural network is a very, very strong method. And if I have a use case where I need such a method, then of course I should apply such a method. We should use the kinds of methods that are well suited for the cases and for the use cases that we have. What's dangerous in my point of view is that due to this strong hype and all this media echo, all the deep technologies received, that people start to believe that artificial intelligence means applying deep neural networks. And this, of course, is not true. The field of artificial intelligence is much broader than all what we see in artificial neural networks and in deep neural networks. And we always have to keep in mind that different methods have their strengths on different use cases. And we have to understand which methods to apply when. And that's, of course, our job as researchers in the field to have this knowledge and to know what methods to apply. And we also have to explain our customers and the companies who want to work with these methods what these different strengths and weaknesses of the different methods are. So I think what's important to understand, because we had this discussion what the customer has to know, and do they have to understand the algorithms, or are they just interested in results? My personal point of view is they do not really care about the method, but it's very important for them to understand what the specific method can do. We sometimes observe customers who believe that an artificial intelligence method is able to gain knowledge out of nothing. And this, of course, is not true. This is not possible. And we have to also make our clients or the companies understand what a method can do and what a method cannot do, and then it's easy to choose the right method for the right task.
Michael, thank you very much, Stefan. Michael, your hand was risen before. Do you have some additional things?
In the meanwhile, Stefan more or less added what I intended to add. Simply, I think it depends on the task that should be solved well, which kind of method seems especially suited, and especially in the field of industrial processes and production. It's pretty often sensor data which we are tackling and which are the basis of modeling and optimization. And in those cases, things are different, which techniques to prefer, especially if there is background in natural science and mechatronic systems. So we pretty often made the observation that not only in terms of interpretability, but also in terms of achievable results, and especially with respect to generalization, that, for example, genetic programming models perform significantly better than neural networks. On the other hand, as Stefan already mentioned, if it comes to unstructured data and computer visions, of course, there were huge successes that could use parallel hardware and achieve good results. But in industry, that's one out of many tasks that can be solved, and not the major thing like it is in the smartphone industry, for example, where it's mainly unstructured data.
Okay, thank you. Dr. Filipic, do you have additional points?
Yes, just to add a bit of a historic perspective to what we are just discussing. So this danger of, assuming that certain methodology is AI entirely, it's actually nothing new. So decades ago, there was one of the first successful applications of AI, for example, were the expert systems. And there was a period of time when these were very, very popular. So this was even used for commercializing various software techniques. So many programs that were not expert systems, in fact, were sold as expert systems because this was very popular at that time. So then later on, it was and you can still read this. So many people were just understanding AI as, for example, machine learning. And so there's a lot of warnings. Okay, it's much more than that. It's not just machine learning. And now, of course, everything tends to be like more in the style of deep techniques. I think it's just, I mean, for those working in the area, should be like acting at their every possibility. I mean, it's education, it is customer relationships, and explaining this situation. But it's nothing new. This danger is nothing new.
Okay, thank you. So I also want to motivate our audience to ask some questions. And now I ask in the round, is there anybody who wants to ask something? Okay, doesn't seem so. So, but I have enough questions for you. I want to also then connect to your answer you gave me. So you talked about it's not just about machine learning. Yeah? So can those PA methods also be used to map a kind of experience of experts in the respective application areas too? Is there a possibility to also learn from the experience of the human experts, not just from the data? Who wants to answer?
Yeah, I think I can answer something to that. Of course, yes, this is possible in many different ways. First of all, if we have a look at supervised learning, then we need some kind of labeled data. Yeah? So, and who is usually labeling this data on the first hand? It's human experts who say, well, this is that kind of class, for example, if it comes to classification problem or another kind of a class. Yeah? So the data that we use as an input for our learning systems usually is data from human experts. On the other hand, we can also have a look at specific capabilities of methods. For example, Michael mentioned genetic programming, and in genetic programming, where you try to learn a formula to predict the specific data that you observed, you can also think about integrating a predefined structure into this formula, which is also a form of integrating prior knowledge. And we have a whole field of transfer learning, how to transform a model and a structure that you learn from one usage scenario to another usage scenario. So I think there are many different ways how to incorporate previous knowledge. And it depends, of course, on the method, how you do that, and how well this works. But of course, the AI methods, from my point of view, are always depending on some data, some prior knowledge that they can learn from. They are always depending on that.
Mm-hmm. Okay. In my time at Center, we deal with different topics in the field of medical engineering, and especially for physicians, it's very important if they have some expert systems telling them some kinds of diagnosis, for example, how the system comes to the solution, how the system comes to the prediction or whatever it is. So how important is it for your applications in the industry to have models that are able to explain how the solution is calculated or how it is get? Who wants to answer from you? Is it important for the industry, explainability of the models or of the methods you use?
Maybe I can start here, because I think there are several aspects which count if interpretability and explainability is of especial interest, and it also is somehow related to the last topic from my point of view. If you want to put the human expert in the loop and somehow integrate a priori knowledge or domain knowledge, it is essential to be able to understand or interpret the machine output, or what the model wants to tell us from the machine side, in order to integrate the human knowledge part. So in order to put the human into the loop, and that's one of many trends in research for human-computer interaction, which also reflects prescriptive analytics solutions, or from a strategic level, as it has been said throughout the talk, also from all colleagues, more or less, to have this digital twin or simulation-based techniques to say the what-if scenarios, which have influence maybe on the management level. So what to do, what to invest in, which way should I design my shop floor or whatever. It's essential to be able to understand the proposed model or scenario.
Mm-hmm. Okay, thank you. All the presentations dealt with the topic of optimization in different aspects, for efficient product quality control, for recommending optimal decisions in dynamic environments, and so on. So what does optimization mean for you and your applications now, and especially then in future, if you think if you have your systems established in a more intensive way in the production process, what is the future perspective? Maybe I may start now with Michael Bögl.
I think that these systems can then be, perhaps even if you take adaptOp, can even be more tightly integrated in the production system. It's not an optimization that runs somewhere besides and is used with more or less success, but it can be really integrated into the processes of the company, for example. They fit naturally in there. They run seamlessly and constantly give new results as the environment changes, for example. And these results are seamlessly integrated in the production process.
Okay, thank you. Dr. Filipic, what's your opinion to that?
Sure. I mean, optimization is important, but I would emphasize again the importance of the language. I mean, if you optimization can be considered from various perspectives, either strictly technically, mathematically, really starting with a well-defined problem. On the other hand, if you go to a customer, in particular to higher levels, it may be achieving some high-level goals in the best possible ways. And of course, there is a variety, I mean, the whole spectrum of optimization challenges, not to mention methodologies. So yes, I think it is important. It is coming into applications, and this will be happening in the future as well in various forms. And there are, on one hand, some of them that do not require, let's say, explainability if it is just setting certain values or so. But when it comes to supporting decisions, it is very, very important that it is transparent, in a way, explainable. And again, I could provide numerous examples of one and the other group. But for example, just to mention those that require understandability and explainability, in one of our projects, we were making a prediction on what to do. This was related to a steel plant. So in the rolling mill, they have a decision to do every day what to do with this emulsion. And the decision is done based on the measurement of various physical and chemical properties of this liquid, of this emulsion. And they had a lot of examples from the past, and they were specifically interested in producing, let's say, a decision model for the actions on this problem. And the situation was critical because the expert, an experienced operator, was about to retire, and they had no one to replace him. So they really provided us with all this data, and the result was a decision model. But of course, for this one, it was not just enough to say, okay, this needs to be done today. They verified it very systematically. Actually, it was decision trees. So they looked at the way of, coming from the, let's say, results of measurements to the decision. So the transparency of this model was very, very relevant to them. They did not adopt it until they were, let's say, convinced it well reflects the knowledge of the expert who was retiring. Yeah.
Okay, thank you. Stefan, what do you think of this future aspects of optimization?
Well, I would say the future aspect of the optimization for me would be that we see an optimization system as a supporting system for human operators. Today, and the example that Professor Filipic just told is a brilliant one, I think, because we see the situation many times that there are human experts who do the decisions in the process, and they do that for many years. They are very skilled, very experienced, and it's very hard to get an algorithm to an equal level of quality in these decision processes. But the problem is that these people to need many years to gain this level of experience, and they are not willing to do this job for an infinite amount of time, because at some time maybe they change their job or they go into retirement or whatsoever, and then we need to try to provide algorithms and methods who can jump in and who can take a part of this decision process and help other humans to do the job and to control the processes quite well. And I think that's the job that we need to do, and that's also what we are currently working on.
And maybe not everybody wants to offer his experience to a machine. That's also, I think, an important point, that it isn't always so easy that people think, for example, that they lose their jobs if they have machines doing some decisions or proposing some decisions, maybe. Okay, so for my last question, well, during my preparation, I learned that in Optimizer's world, many is more than multi. So in the sense of multi and many objective optimization, how can diametrically opposed goals also be represented in the models, and how can they be optimized? So we have seen in the presentations, okay, there was one goal, and how do you handle those opposed goals? Who wants to answer?
I can start. Professor Filipic mentioned the way of showing non-dominated solutions as Pareto optimal solutions in multi-objective optimization. And if you have more than one objective, it's more about finding best compromises. And solutions on a Pareto optimal front are best compromises. And then again, you need human expertise for decision making, because then the issue is to say which is my preferred way of those best possible compromises, and a solution method could achieve.
Okay. Dr. Filipic, what do you think?
Yeah, sure. I mean, multi-objective is one of my favorites. So, I mean, this difference between multi and many is just a terminological issue. So there is often a debate, yes, in particular between decision-making community and multi-objective optimization community. They handle. I mean, they only distinguish between single and multi-objective, but in let's say population-based multi-objective optimization, there is a distinction between multi and many because of the hardness of the problem. This has to do with the development of the algorithms. So everything that is, let's say, 2 and 3 is, for the sake of distinction, considered as multi, and what is more than 3, so starting with 4, is many. And this had to do with the let's say, first generations of the algorithms were quite successful, of course, on the problems of lower dimensionality in terms of objectives. Then they realized that starting with 4, it becomes much more difficult. So they introduced new concepts in solving these problems. So that's the distinction between multi and many. Yes, I mean, the methodological point of view is this. In practice, of course, at the end, you need to adopt one solution. So, but if there is no, let's say, knowledge about the preferences or the weights between the conflicting objectives, then this multi-objective way of solving problems that provides you with the trade-offs first is a very useful tool on your way to selecting the final solution. Because once you have all the trade-offs, the compromises identified through a Pareto front approximation, you really have a better insight into a problem. You can see how you can trade between the objectives. And then, of course, this is just let's say, a step to do the final decision making. I mean, of course, it is a very simple thing. If you know the weights or the preferences in advance, then you can go for a simpler, let's say, weighted sum or some other method of reducing the number of objectives and solving the problem in a single objective manner. But yes, it is useful for providing better insight into the problem as well, not just solving the problem itself.
Thank you very much, Dr. Filipic. So I must say we have found an optimal solution for today's event because we are just in time as far as I can see. And now it's my turn just to thank you all for your presentations, for the discussions, for doing really a great job, and to show how these different methods can be used in industry and in production. I just want now to hand over to Sonja Mündel to speak some additional word to you. Please, Sonja.
Okay, at the end, I only want to inform about 3 events this year. The first, can you share it, please, Magdalena? Yeah, it will be the 3rd event on 10 June this year, Prescriptive Analytics, and it will be the last one of the series of the Prescriptive Analytics which we have this year. Well, then in May, I think we will have another in-breakfast with a Softwarepark Hagenberg partner called Limit Security. And in June, we will have, as I said it again, I think in November we will have the ISM, Professor Affenzeller talked about it, here in Hagenberg, and I hope it will be live. That was all. I hope you enjoyed our expert event today, and yes, I only had to say goodbye. And I hope I will see you all again here in Hagenberg. Thank you very much.
Thank you very much too.
You.
Bye. Thank you.
Bye.
Okay.
Bye-bye, thank you.
All right. Gut. Da hat nur wer aufgezeigt jetzt. Also nein.
Das war ich wollte jetzt alle Möglichkeiten noch einmal ausprobieren, was man da hat.
Achso, Josef, grüß dich. Ja,
Machen wir nur eine Runde.
zwischendurch.